All right, so we have this problem, matrix diagonal sum. So we have a square matrix and we want to return the sum of the matrix diagonals. So both diagonals, as we can see in this picture. But only include the sum of the elements on the secondary diagonal that are not part of the primary diagonal. And so you can see this playing out in these two examples here, where if the you have this case here where you have the primary diagonal and the secondary diagonal, and they intersect at 5, and you only include 5 once in the sum. Whereas here in this matrix, there's no overlap between the two diagonals, and so you just add all of them up. So we can immediately see here that okay, is there anything important in the constraints? Not really, it's all pretty standard. Okay. So, we do see there's a special case that we need to be aware of here, of whether these diagonals intersect or not. And if they do intersect, we need to make sure that that middle element is only counted once. So, one way to do this is to just get the sum of both diagonals, and then if we're in a case where there is an overlap, then just subtract this. And we can see that they're going to overlap precisely when the number of rows, which is the same as the number of columns, when that number is odd. When that number is odd, we're going to get an overlap. When it's even, there's not going to be any overlap. So we need to, so we can just add up both diagonals, and then if the number of rows and columns is odd, just subtract the middle element. So that's what our code is going to look like. So let's write it out. I'm going to write this out by hand because it helps me learn and I like to do it. So the total is going to start at 0. I'm not going to use like NumPy or anything for this. Like you can, because NumPy has built-in functions for computing diagonals of matrices, so that can be useful here. But it doesn't really save too much in terms of like writing out the code, so I'm not going to do that. But you can if you want. So the total will be 0, and then n is going to be the length of, it's going to be the number of rows, which is the same as the number of columns, which is going to be the length of mat. And we are going to use this, which is why I'm defining it. So for I in enumerate mat. So you could just do for I in range length mat if you want. I don't know. This is a little nicer because range length, you're nesting a function. So sometimes this can look nicer if you want, but maybe you don't like the underscore. I don't know. It really doesn't matter. So what we have to do is, okay, so our gut reaction is, okay, so we want to get this sum of the diagonal. So let's loop through and get this first diagonal and add all of those together. And then let's loop through and get the secondary diagonal and add all of those up. But we can actually do these all at the same time in this single loop here, because what is the pattern for like what the indices look like? So when you're looping for I from 0 to n minus 1, because that's how indices work in Python. For the primary diagonal, we're going to add up the 0, 0 entry, then the 1, 1 entry. Basically, you're just going to add up the entry, the I, comma I entry for every I, and add all those up. But then what about the secondary diagonal? So the index of the row is going to be the same thing. It's going to go from 0 to n minus 1. But the column index is, it's going to go backwards. So it's going to go from n-1 down to 0. And that's actually something that we can like implement pretty quickly, because that's just n-1 minus I. Because that will start at n-1, and then it'll go to n-2, n-3, n-4, and it'll go backwards all the way down to index 0 at the very end. So what we're doing here at the very end is the total will be plus equal mat I plus mat I n-1 minus I. And this first term here is adding up the entry in the primary diagonal, and the second term here is adding up the entry in the secondary diagonal. And you do have to think a little bit to make sure that you're getting this index right here, and make sure that you're not getting an off by 1 error, because those are things you need to look out for. But if you think through it like we have, then you're going to be good. Okay, so this is how to get the sum of the diagonals. Now we have to deal with that case of that middle case of what we do with that middle entry. And that only comes up if the dimensions of the matrix are odd. So and we can check for things being odd by dividing by 2 and seeing if that remainder is 0. Or if it's 1. It's going to be 0 if it's even, or 1 if it's odd. So if it's equal to 1, meaning that we're odd, then we're going to... Then what this means is that in the previous loop, we counted that middle entry twice. So what we have to do is we need to take that middle entry and we need to subtract 1 copy of it. And, well, wait, what is the index of this middle entry? So turns out it is going to be n divided by floor division n divided by 2. So you're going to take n, divide it by 2, and round that number down. And you are going to have to round down because in this case the length of the matrix is odd, and so dividing by 2 is not going to give you a whole number, and so you will need to round down in order to get an integer, which is a valid index. But how do we know for sure that this is the middle index? If you can just think about it a little bit and be like, okay, well this is a 3 by 3 matrix, and here this middle entry has index 1, 1, and 3. When you take 3 divided by 2 and do floor division, you get 1, because 3 divided by 2 is 1.5. Floor it, and you get 1. And then you can look at, okay, so what if it were a 5 by 5 matrix? Then the middle entry would be index 2. 5 divided by 2 is 2.5. Round it down to get 2. So, if you're trying to be like Sonic and go fast, and you especially in an interview or something, and you could just look at those cases and be like, okay, we're good to go. I should probably turn the total. Okay, so yeah, but if you want to be very convinced of the fact that taking this floor division, taking this floor after divided by 2 gives you exactly the index you're looking for, we can actually prove that. And I'm going to do this because I like opportunities to do proofs. Okay. And if you're fully convinced, you can just skip over this, but I'm going to do this because I like it. Okay. So when n is odd, n floor division 2 is the index of the middle element. I am writing pretty sloppy here. Okay. All right, so let's prove this. Okay. So, suppose n is odd. Then, that means that n is equal to 2m plus 1 for some m between well, start like this. For some integer m, which is at least 1. Well, it's at least 0. Is that right? When m is 0, n equals 1. No, that's trivial. Let's just say n greater than 0. Okay, cool. It really doesn't matter too much. Okay. Okay. So let's see here. The middle number between 1 and n is, what is going to be the middle number between 1 and n? Okay, so this is going to be n plus 1. Why is this true? This is true because n is 2m plus 1, and so we can sort of see the, if you're looking at this from a number line, you have like n, or you would have m values and another m values, and then you would have just the one in the middle there. So what is the middle number? If we're considering these like integers 1 through n, then the middle number here is going to be m plus 1. Because the length of this is m. Okay. However, indices start at 0, so the desired middle number is not m plus 1, but m. Okay, so this is the key, is that if n is odd, you write n as 2m plus 1, and the index that you're looking for is m in this equation. Okay, so how do we get m? So let's look at n floor division 2. So this, by definition, you take n divided by 2, and then you take floor division. Okay, but n, we know, is 2m plus 1. And this is being divided by 2, and then we floor it. Okay, so this is going to be, well, inside this floor division, we can divide by 2. So 2m divided by 2 is going to be m plus 1/2. And when you take the floor of this, the 1/2, like m is an integer, and so the floor has no effect on m. The only thing it impacts is this 1/2, which will go down to 0. So this is precisely m. Okay. So n floor division 2 is equal to m, which is the desired index of the middle number, or middle element. Well, the element is a number, so it doesn't really matter. But yeah, the point here is that this gives you a proof that n floor division 2 is precisely what we're looking for. Okay, so there we go. Let's actually code this up now. Okay, so I'm going to start the total at 0. I'm going to have the length of n be stored in matrix. For each index in the matrix, we're going to add to the total the entry in the primary diagonal and then the entry in the secondary diagonal. So this is n minus 1 minus I. Okay, so there we go. Once you do that loop, you'll get the sum of the diagonals. And then if n division with remainder 2 equals 1, meaning that dividing n by 2 and taking the remainder gives you 1, meaning that this is an odd number, then we have added the middle element twice, and so we need to remove it once. So n floor division 2, n floor division 2, that is going to be the index of that middle entry. So we do that, then at the end, we return the total. And that's all we have to do. Now this is wrong, because I don't know how to code. But now I do. Yeah, all right. So there we go. That is our solution. I think if you're going fast, it can be a little tricky to wrap your head around why or how you exactly get the index of the middle element. But I think that's, I would consider that the trickiest part of this problem, and otherwise the rest of it is more straightforward. And so there you go. That's how you do this.